Okay, so here I've got a power cycle. Okay, notice I've got Q in, Q out, specific amount at a specific temperature, and of course I got a work of the cycle, and that's got to, that's got to be going out. Okay, my Q occurs at 600, but I don't really know what direction it is, what value it is, and that's what we're trying to find. Let's find a range of values and a direction for that Q3. And then after that, let's go ahead and find the best efficiency we possibly can. So we're going to start with the first law, which states that basically the work of the cycle equals Q of the cycle, where Q of the cycle is Q1, which is in, minus Q2, right? Because that one's out. And then I've got Q3. I don't know. I'll just assume it's positive. If I get a negative answer, then I know it's negative, right? So I'll assume it's in. If I get negative, then it's out, okay? So plugging these values in, I have 600 Q1 minus 400 Q2 plus Q3. And again, that's got to equal the work of the cycle. Now, this has to be positive. Because it's a power cycle, work of the cycle has to be positive. So work of the cycle is greater than 0. Therefore, Q3 has to be greater than negative 200, right? Because when this equals 200, then that equals 0. As long as it's bigger than negative 200, then I'm fine, right? So if it's 0, then it's 200, that's positive. If it's positive 200, then I have 400, again, a positive number. So as long as this is greater than negative 200, everything's okay. Okay, so that gives us one bound. We got to find another one, okay? And the other bound we're going to use is using my Clausius inequality, where I have sigma of the cycle equals, and you've seen this is what's in the book, del Q over T. And what this is essentially is it's summing up for a cycle the Q's over the temperatures that occur at. So I've got 3 of these here. So I don't have to do an integral. I can do them, independently, right? Which is to say I've got, again, Qn, right? So that's going to be 600 over 1,000, right? 600 over 1,000. 400 over 800, that's going to be minus 400 over 800, right? And then this Q3, which again, I'll just assume is positive. If I'm wrong, I'll get a negative answer. We can work from there. So again, we're trying to figure out what that direction is. So I'll just say plus 300 over, or I'm sorry, Q3 over 600, okay? And I'm going to rearrange this a little bit so I can kind of get rid of this negative value here. And I'll say sigma of the cycle. So if I take that negative here, I'm flipping all the signs over here. Okay, so I get negative 0.6 plus 0.5 minus Q3 over 600. Right? So again, it's just kind of flipping the signs on here and getting that in a more usable term, because again, what I know is that my sigma has to be greater than 0. Okay? For that to be greater than 0, that means Q3 has to be less than negative 60, right? Because I have this plus this gives me negative 0.1. So I have to add 0.1, so negative gives me that positive 0.1 and get back to 0. Okay, it can be anything smaller than that. If it's negative 600, right? Then I have negative 0.1 plus 1 gives me a positive 0.9. So as long as this is less than negative 60, life is good for our situation. Therefore, what I have here is negative 200 BTUs. And negative 60 BTUs. That's the range that Q3 can be. Therefore, it is Q out. Okay, that's heat out of the system because it's a negative value. So I definitely know the direction is going out on this guy. Now the final question is, hey, let's find the theoretical thermal efficiency, right? Which is eta max. Now this occurs at this situation. When sigma is 0, that is the best case scenario. So for that system, I know that Q3 equals 60. Therefore, okay, I get the work of the cycle. So basically, I get Q1 minus Q2. That'll be minus Q3 because I know that Q is out over Q in, which is really just Q1. So what do I get here? Well, I get Q1 again is 600. That's what's in. Minus what's out, which is minus 400. And then minus 60. This is the best case scenario right there. All over 600, which is what Q in is. And from that, I get the maximum thermal efficiency to be about 23.3%. Okay, so again, use the first law to bound Q, see what the bottom of Q is. Okay, then use the second law equation here to figure out what the upper bound of Q3 is. From that, I know that it's Q out. Once I know that, then I can find the maximum. Again, using what's going on here, this is the best case scenario that I can have for my system here.